Today, I will continue our discussion on how to choose the parameters. For this session is the exponent, private exponent chosen by Alice or Bob. As you may recall from your Diffie-Hellman protocol discussion, both Alice and Bob, they pick a random number x and y respectively. Alice computes g power x mod p, Bob computes g power y mod p, and they both exchange the capital A and B respectively, and then they combine that with their individual private. See here, Alice takes Bob's public key capital B and writes it to her capital X. Symmetrically, Bob does that as well. In the end, they both have the same key. The question is how large this X can be, or how small X can be. I would like to shed some light on that. The way I wanted to approach it is I will use a real implementation, Bouncy Castle implementation, and talk about how Bouncy Castle handles the size of X and Y. Okay, so let's get straight into the Bouncy Castle implementation. So Bouncy Castle is open source, so you could take a look at the open source GitHub repository, for example, and you will see a file called dhparameters.java, and there is a class dhparameters inside that file. It has a bunch of variables like G, P, Q, J, and so on. We are familiar with most of them from our discussion in the past. We do know P and Q are primes, right? They both are primes. We do know P is equal to J times Q plus 1. In the case of regular safe prime, J is equal to 2, safe prime case, right? In generalized safe prime, or some people call it DSA, the digital signature algorithm safe prime, J is much larger than 2, meaning Q will be small in that case. So PQGJ is pretty clear. G is a generator, of course. See, G is a generator of the subgroup of order Q. Okay, that's basically the setup. What about M and L? We have not really used M and L. Okay, it turned out that at least in Bouncy Castle, the user of the dhparameters class can specify what is the maximum or what is the minimum size for the exponent. That the small m that you're seeing is minimum size. Okay, you could say I would like to have a minimum of 200 bits for my exponent, or 100 bits, or whatever you could specify. Of course, there's some limit, lower limit. If you are not careful, you will be vulnerable. I will show you that. But essentially, m is the minimum length of your exponent. Okay. What about your L here? Okay, so m is the minimum length of the exponent, right? What about L? L is actually another limit. You could say don't go more than that. You could say maximum. You can imagine like this: maximum length or limit, right, of the exponent. So you could think like that way: maximum length or the limit. Okay, so I will now explain to you how Bouncy Castle handles this. I will not talk about the DH validation parameters in this session. It's important, but it's not important for this particular session. Okay, so what I'm going to do is I will highlight some important properties of M and L in this class. So what they do is, here is the constructor, right? Default constructor is not there as far as I can see. Here is a constructor with 2 arguments, P and G. That means your Q is null in this case, as you can see, null. And then there is another constructor. If you know P, Q, G, you could use this constructor. If you know P, Q, G, and L, the limit I mentioned, you could use this constructor, right? Constructors call other constructors. As you can see, there's this command. So in the end, they all call this large one, actually, which has all the arguments P, Q, G, M, L, J. Okay, so if you set the value of L, by default L is 0, right? If you set it to non-zero value, it checks here. Okay, if you can't select the value more than the size of the modulus that we are working with, so that's not allowed. and you can't select a value of L smaller than the minimum value. That makes sense, right? M is the minimum value, so it should not be anything smaller than L, smaller than M rather. Okay, so what about M? M is the minimum value. Of course, we don't want M to be more than the modular size also. So that's very basic check here, okay? And then there are a bunch of getters method, like, get P, get G, Q, J, and M, and L, okay? So what is interesting for us is to look at the exponent generation part, okay? Where is the exponent generated? I will show you the real code, right? It's fun to see the real code. So here is the calculate private method, which does generate the exponent X that I have shown on the slide. So we can see everything in action. So as you can see here, the first argument is called dh params. It calls the method called get L to get the limit. The limit is the maximum limit, okay? So what it does is, there's a little check here. It checks whether the user has asked for a limit or not, or set the limit or not. If the user has set the limit, which means limit is not equal to 0, in that case, you can leave this min byte and this WAF utility. It's just to make sure that the numbers are the random number X doesn't have a lot of ones, otherwise it will spend time on multiplication. So you can leave out this part. That's important, but it's not necessary for our talk here. Usually the randomly generated X will have this property, so we don't have to do much check here. But anyway, Bouncy Castle does it for defense in-depth programming paradigm, so that's fine. Okay, anyway, so coming back to this X generation, how is an X generated? So as you can see, it is generated using the Java's big integer class, and it specifies the random object. This is the random object, right? What about the limit? That's the minimum. Let me rephrase this. The limit is the number of bits the exponent you wanted to have. Okay, it's not minimum. It is the number of bits you want to have. Suppose you say I want to have an exponent of say 256 bit. Then you would set limit to be 256. As you can see, it will set the 255th bit on. That's the meaning of having a 256 bit, right? So because we start with the index of 0. Okay, so this is how your X is selected when you know the max limit for your exponent. Okay. On the other hand, if you do not set the limit, that means the limit is 0. So let me explain that first. In that case, it comes to the else part, of course, right? Because otherwise it's done here, return. It comes to the else part, and it goes to the for loop here. As you can see here, it is calling the create random in range method. What it means is that it will select a random number between min and the max. Okay, what is min now and what is max now? Let's dive into that details. Okay, min is the member variable m that I talked about. What is the minimum size you would like to have, right? And if you do not set that, it will choose the default one, right? The default one is where was the default one? The default one was about 160 bit. Actually, in literature, it's recommended to use more than at least 256 bits. In some cases, 224 bits, but in general, the recommendation seems to be about 256 bits. Okay, at least 256 bits to be more precise. Anyway, so that's the minimum, and the maximum is basically where is maximum coming from? The maximum is actually coming from q minus 2. Why is the maximum value bounded by q minus 2? Now we have to recall our definitions of p and q and j and all those. So we have this discussion, right? What is the subgroup we are generating? We are generating a subgroup of order q. Okay, that means it is enough to raise the exponent to the max length of q. Okay, that's basically good enough. That's the reason why they take the size of q and subtract by 2. If you just subtract by 1, the value will be 1 because of the fact that q can be p when q is null. That's the reason why they would do q dot subtract 2. Okay. Anyway, that's a further more detail. But at this point, it's clear that the value of the exponent is actually bounded by the limit that the user is set, or it will select something between min and max. Min is the minimum length, which is 160-bit, and the max is the order of the is about the order of the subgroup Q. Okay, that's basically it. So if the subgroup order is, what if the order of the subgroup is say 256-bit? Then it's clear that your max is also 256, right? So you will be getting an exponent at most 256-bit length. Okay, that's basically what we are talking about. If you set the limit explicitly to 256-bit, of course we are not even coming here. We already chosen in that case an x which is at most 256-bit long. Okay, otherwise this is basically it. In the case of safe prime, our j is 2, right? And q is actually very, very large. It's not 256 order. It's about the order of q is actually almost the size of p, approximately the size of p. Okay, and when p is very large, it doesn't matter whether p or p by 2, doesn't matter. But anyway, order of q is really, really large number when we use j equal to 2 in the case of regular safe prime. Okay, so what it means now is that the exponent that we will be selecting using this code will also be very large, right? Because we are selecting a number in this range, right, between min and max. And as I said, min is 160-bit, maximum is the order of the subgroup Q. If the subgroup Q is a really large subgroup, then you will get a large exponent, very likely. Okay. All right. So, but if you don't like the very large exponent, what can you do? You could simply set your limit, and you will be here, right? You will set a limit which is not equal to 0. Then you will come inside, and you will be guaranteed to have an exponent of exactly the size that you prefer to have. You say, I want to have 256-bit. Doesn't matter whether I'm working with safe prime or a generalized safe prime. I would like to have 256-bit. Then this is basically it. It will select it for you. Okay. Okay, so what happens if you're not careful and select a small exponent? That's where the interesting problems emerge from a security point of view. So I briefly talked about the baby step, giant step algorithm. There's also other names for that. That's a Shank algorithm. It's an interesting idea. So there, if the exponent size is small, you could break it. So what I mean by breaking it, let me quickly show you the idea, and then I will talk about an implementation. Okay. So what is the discrete logarithm problem in the context of Diffie-Hellman? Basically, given h, given g and p, our goal is to find x, right? That's basically what on the slides we were using capital A for the public key sent by Alice and capital B for Bob, but essentially this is the high level generalization. Okay, so how do we go about this? It turned out that this problem can be solved using baby step, giant step idea of when there is a limit for the x. Okay, if you choose an x, say for example, x is bounded by say in this toy example, I'm going to choose x bounded by 2 power 40. It doesn't mean that we are going to try 2 power 40 steps to solve it. Actually, we can solve it in 2 power 20 steps. So it's kind of a square root attack. Okay, it's like a birthday paradox kind of idea. You look for some kind of a collusion, and then you'll find the x. Actually, what it means to say is that if the exponent x is bounded by, say, 256-bit, how many attempts then I have to make? Then I have to make about 2 power 128 bits. That's a lot of attempts I have to make. 2 power 128 attempts I have to make if my x is bounded by 256-bit. So the idea is that you choose an x, the limit, if you remember from the Bouncy Castle discussion, you want to have the limit to be large enough that an attacker has to do at least 2 power 128 steps. That's a lot of steps an attacker has to make. Okay, so what I'm trying to say is that you want to be able to choose an x, right? Choose x that is difficult for an attacker. Okay, what it means to say difficult for an attacker, if your x is size of x, actually, if the size of x is basically about how many steps I said. If it is bounded by, say, 256-bit, right? How many steps the attacker has to do? The attacker has to work, for example, about 128, 2 power 128 steps. Okay, that's a lot of steps for him. He has to do 2 power 128 computations at a very, very high level. Okay, that's basically the idea of choosing the limit. If you choose it too small, of course, you could build a little table and brute force it very quickly. But if you choose x to be very, very large, then you will spend time in doing the computations. Actually, exponents take time. So you could find a middle ground by choosing an x of size 256-bit. That's perfectly fine, as far as we know in today's standard. Of course, you would like to make it configurable, so you could quickly change it to a slightly higher number if new attacks emerge. Okay, all right. So that's basically it. And we should see a quick demo of what happens if I choose good G, P, and Q, but my X turned out to be small for some reason. Then it's going to be a very bad consequence. Okay, I will show you the algorithm, and then I actually will show you the details of an implementation. Okay, so this I can skip. Okay, here it is. So the core idea is that, suppose, assume my x is bounded by some 2 power n. Okay, what is n? N could be, say, for example, 128. Okay, in that case, how much work I have to do? I have to do only 2 power 64 work. It's still a fair amount of work on my laptop, but for more powerful computers, the goal is to choose the x that's difficult for people to try this brute force attack. Anyway, for the brute force, for the attack that I'm going to show now, I will treat my x to be much smaller, because otherwise my demo will take long time. So the idea is that, let's assume x is bounded by some number b. Okay, so what are we going to do? In that case, we can write our x as a linear combination of x0, b, and x1. We don't know x0, we don't know x1. We do know b. As I said, b is some square root of 2 power n, right? N could be 40. In this case, it's much easier if we choose n is 40. It means the b is 2 power 20. So what are we going to do next? We rewrite this equation and do some simple reorganization. Then we get x by g power x1 is same as g power b x0. So what we will do now is we will be preparing a table. We will try all possible x1s and compute h by g power x1 for all possible x1s, right? What are the possible values of x1? We can clearly see here x0 and x1 are bounded by 0 to b minus 1. So we will build a table, and then we search for different x0 values. We compute g power b x0 for different x0s. As soon as we find the collusion, we know we found x0 and x1, because we have this table which maps us from h by g power x power I to x power I. So we found x0 and x1. Once you know x0, x1, we solve the problem, because we already found the b. B is something we have chosen. So we know x0, x1, and b. We solve the discrete logarithm problem. Okay, for x that are bounded by some reasonably small number. Okay. What is interesting though is that it's square root. Okay, if your x is 100-bit, the attacker need not do 2 power 100 work. He has to only do 2 power 50 work. Okay, that's basically the benefit of this idea of this nice algorithm. Okay, so having said that, let's get into the implementation details and have a look at this. From a Python perspective, I wanted to show you how it look like. Okay, so I call it the Shank.py, which is basically what I learned is that he's one of the inventors of this. It looks like others have also invented this algorithm before him, but anyway, that's always the case in many situations. Anyway, so we want to find an x such that h is equal to g power x in mod b. We are given b, g, and h, and we are given the bound, the capital B on the slides is a bound. What I'm going to do is I first prepare the table that I talked about, right? I prepare the table g power x1. Let me draw this a little bit. So what am I doing here? I'm actually building a hash table. What are the elements of the hash table? The hash table has g power x1, right? G power x1. h, and then I compute the inverse of it. Okay, I compute the inverse of I'll put like this. Okay, I compute the inverse of g power x1 and then multiply it by h. That will be my key, and then my value is x1. That's what I'm doing here in this portion of the code. Okay, I build this table. It makes much sense if I write it like this. Although you should be careful that there's no notion of division in a bounded model arithmetic. It's multiplicative inverse. Okay, so I do this, and then once I'm done for all possible x1s, what are the possible values of x1s? I'm doing it from 0 to bound. And then I go out of the loop, right? I go out of the loop to do what? To do the search part. This is the table building part. In the search part, I will select different x0s and compute. What am I computing? I'm computing g power b, right? That's the g power b part. The g raised to b is g power b in mod p, and I raise that to x0. X0 is also bounded by bound. So I check whether g power b x0 check. Let's call this value t. Okay, check d. The hash table contains t. Okay, if it is, what can we say? We know that we found a collision. I explained in the algorithm slides. So once you found the collision, you know x0, x1, and b. All you have to do is just compute all of this here, right? x0 bound and x1. Okay, so this basically solves the discrete logarithm problem for small groups. Okay, in general, small groups. So if you wanted to run this quickly, so let's do that. Maybe we should take a toy example first. Let's do a simple toy example. Let's generate a cyclic group of order 12, right? This is the cyclic group of order 12. What is the example I would like to show you? Maybe I will select like this. We do know 2 power 1, 3, 4, 5. 2 power 5 is 6 in mod 13, right? 2 power 5 is 32. 32 mod 13 is 6. So can we find out the value 5? Given value 6, value, generated 2, can we find the power exponent 5? Can we do that? Let's quickly check it using this Shank algorithm. Okay, so it's going to say, what is your group modulus 13? What are the, I'm going to work with the group 2 generator. This is not a safe prime. I'm just using regular prime. So we need to find the exponent for the value 6. Okay, that's what I'm going to ask for. And it's asking the number of exponent bits. Okay, in this case, it's a tiny group, so it should be okay if I give 4-bit, because it's the order of the group is 12, and the square root of 12 is actually 3, more than 3. So I will do a floor to get 4. Okay, so I will do this very simple. Okay, it's done. It built a hash table and it tells us that it must be 5, meaning 2 power 5. We can quickly check that, of course. Print 2 power 5 mod 13, right? Hopefully it will come back to 6. Yeah, it does come back to 6. So what did we find? We found the exponent of the private key. So basically in this case, we just ran the discrete logarithm problem and solved this. So can we apply now on large primes and what have you? So what I did was actually I copied the RFC, right? I have the P, Q, and G, and I want to show you that you can actually solve this problem for real P's and Q's and G's that you see in the internet. For as long as your exponent is small, of course. That's the reason you want to be very careful. It's not just selecting P, Q, G. It's more than that, right? You want to be careful with your exponent as well. So how do we do that? So let's quickly make use of this PQG, and let's take it simple. Let's say my exponent length is only 20-bit. The limit L, I will add a limit $L is 20, which is extremely small, of course. Oh, $L. Okay, so now let's try this thing on this. Have our program run. Okay, so Of course, you will never print the private key on the screen, but I wanted to show you how easy it is for me now to apply this Shank algorithm. So I will be selecting, say, for example, Alice's public key, and I will show you that the algorithm can find the same private key that you're seeing. Okay, so I need to do some simple things. Now, first I need to select the public parameters. What are the public parameters? The public parameters include the group P. So now I need to select the group P first, right? So I will select the group P, which is now big integer, regular integer, and I will select it's the same number, it just shown as integer instead of X. And then I also need, what do I need? I need Alice's public key, right? So this is my H in the Python world that I have shown. Okay, what was my generator in this case? We need a group generator also, right? The generator is small, g equal to 2. That's good. In this case, g equal to 2. Okay, so I'm going to use this setup now to find out the private key of Alice. All right, let's try that. Let's just copy this prime. This is the public prime, and then it's asking the group generators 2, and then it's going to ask us the H. Okay, so remember my exponents were really small, right? I only generated a 20-bit exponent. So my limit is extremely simple in this case. So I'm going to just say 20. It's going to build a table of 2 power 10 items. So it's very quickly done, and it solved the problem. It says 714871. Let's see what is Alice's private key. Is it 71? Yep, here you go. Maybe maybe it's not after all Alice, it was more a Bob. Yeah, let me check, what did I copy? 71. Yeah, it's the same number, 714871. It's the same as the number that you're seeing here. The same as the number that you're seeing here. Okay, so we found out very quickly that if the exponent size is small, we can easily solve this problem using Shank's algorithm. So to sum up this discussion, going back to the bigger picture, it is important that when we are choosing the parameters, the value of X is better be at least 256-bit or so. Okay, at least 256-bit. There are some literature, some approaches talking about slightly smaller than 256, like 224-bit. I saw for the DSA algorithm, but in general, the idea is that if you want the hacker to do 2 power 128-bit work, then you want your X to be at least 256-bit. Okay, that's basically the purpose of this demo, and I hope I convinced you the importance of the exponent and how large the exponent has to be.